It was a Tuesday in August of 2012, and at the Jet Propulsion Laboratory in Pasadena, California, a physicist named Ed Stone was drinking bad cafeteria coffee and staring at data that shouldn't have been possible. The numbers on his screen described a boundary, not a line on a map, not a place with a flag or a photograph, but a real, measurable edge in the fabric of space itself. And the spacecraft that had just crossed it had been launched 35 years earlier during the Carter administration, when disco was still on the radio and personal computers were a hobbyist's dream. The coffee was hot, the data was cold, and somewhere beyond Neptune, beyond Pluto, beyond the outermost reach of the sun's magnetic influence, a machine the size of a subcompact car was talking to them. It still is. To understand what was happening at JPL that August, you have to understand the improbability of everything that came before. Voyager 1 was launched on September the 5th, 1977, not as the first spacecraft of its mission, but actually the second, launched 16 days after its twin, Voyager 2, on a faster trajectory. The mission that became Voyager had been conceived in the late 1960s by a young JPL engineer named Gary Flandro, who discovered an extraordinary alignment of the outer planets that occurs once every 176 years. This gravitational highway, a multi-planet slingshot called the Grand Tour, was open from 1977 to 1989, and then it would close for generations. NASA had one window. The 14,000 people worked on the Voyager program across its development. The primary mission cost roughly $865 million at the time, equivalent to well over $3 billion in today's money. And it worked. God, it worked. But that is the history everyone knows. What almost no one remembers is what it felt like to be inside Building 164 at JPL on August the 25th of 2012. What the room sounded like, what the instruments were actually saying, and why the scientists gathered around those terminals were not entirely certain, even that morning, that the moment had already come. The problem was that the heliopause, the boundary where the sun's solar wind gives way to interstellar space, had never been crossed before. No human object had ever left the solar system. When there was no checklist for this, there was no historical reference. The scientists knew roughly what to look for: a sudden change in the density and direction of charged particles, a shift from solar wind particles to the different older particles of the interstellar medium. But the actual boundary turned out to be messy, complicated, more like a coastline than a clean line. Voyager had been lingering near the edge for months, slipping in and out of what some scientists called the Helios Heath, the turbulent frontier zone where the sun's influence was collapsing. Edward Carroll Stone had been the project scientist for Voyager since 1975. He was 66 years old in August of 2012, white-haired and precise, in the way of a man who had spent his entire adult life listening to the universe through instruments he helped design. He had joined the mission when Jimmy Carter was still governor of Georgia, and disco had not yet been invented. He had watched Voyager fly past Jupiter in '79 and seen photographs of the Great Red Storm that nobody alive had seen before. He had watched it pass Saturn in '80, Uranus in '86, Neptune in '89. And then, for 23 years, he had watched it just go. Outward, into silence, still transmitting, still alive. The data Voyager sent home in the summer of 2012 showed something unmistakable. The magnetic field had not changed direction, which confused some scientists who expected it to shift at the boundary. But the density of particles had changed dramatically. Solar wind particles had dropped to near zero. Galactic cosmic rays had surged. On or around August the 25th, the crossing appears to have occurred, though the scientific confirmation would not come until September of 2013, when a paper in the journal Science formally declared it. The uncertainty itself is part of the story. The universe does not post signs. Picture the JPL operations room on a quiet Tuesday. The Deep Space Network, the system of massive radio dishes in California, Spain, and Australia that serves as Earth's ear to the outer solar system, had been tracking Voyager for decades. The signal takes approximately 17 hours to arrive from Voyager 1's distance. 17 hours. A conversation with the spacecraft is not a conversation. It is a series of letters sent to someone who will not write back until tomorrow. The engineers who listened to the data that August were, in a very real sense, reading messages from the recent past. The people in that room were not the people who had launched Voyager. Many of the original mission team were retired or had died. The men and women monitoring the data in 2012 had, some of them, been in elementary school when the spacecraft left Earth. They inherited the mission the way you inherit a family photograph, something precious that was made before you arrived, that you are now responsible for keeping. And here is the detail that almost never gets told. Voyager 1, at that moment, was running on approximately 360 watts of electrical power, less than 4 standard light bulbs. The power came from 3 radioisotope thermoelectric generators, slowly decaying plutonium dioxide, converting heat into electricity. The RTGs produce a little less power every year. By 2025, only 3 scientific instruments would remain operational. By approximately 2036, there will likely not be enough power to run anything at all, and Voyager will continue outward in silence, carrying its golden record into a galaxy that will not care whether anyone is listening. The golden record itself is worth pausing on. It was assembled in 6 weeks in 1977 under the direction of Carl Sagan. It contains 115 images, encoded as analog waveforms, greetings in 55 human languages, the sounds of surf and rain and wind, and a mother's first words to her newborn child. 90 minutes of music including Bach and Beethoven and Chuck Berry, and a plaque with instructions for how to play it. It was not designed to be found. It was designed in case it was. There is a distinction there that says something important about who we were in 1977, and perhaps still are. The distance Voyager 1 had traveled by August of 2012 was approximately 121 astronomical units. 1 astronomical unit being the average distance from the Earth to the Sun, roughly 150 million kilometers. Voyager had covered that distance 121 times over. It was moving at approximately 17 kilometers per second. Even at that speed, it will take approximately 300,000 years to pass within 2 light-years of the nearest star system, Alpha Centauri. Ed Stone, in interviews from that period, often described the mission with a specific phrase. He called Voyager a gift to the future, not to the present. The mission's scientific return had long since paid for itself in data about the outer planets. But the crossing of the heliopause was something different. It was proof of concept for the entire human project. Here was a machine built by people who are now mostly dead or old, running on software that predates the internet, communicating across a distance that would take light itself 17 hours to cross. And it still worked. It crossed into interstellar space, and it called home to say so. In the control rooms and offices of JPL in August of 2012, there was something that the scientists and engineers describe as a complicated feeling. Not pure elation. The data had been ambiguous for months, and formal confirmation was still a year away. Not anticlimax either, because the numbers, when you looked at them carefully, were extraordinary. It was closer to something like awe with a scientific temperament. The kind of feeling you get when you have been working towards something your entire career, and the thing itself turns out to be even more interesting and strange than the models predicted. One engineer who worked on the plasma wave instrument that detected the density shift later said that the moment he understood what he was looking at, he sat very still for a long time before saying anything. He wanted to be sure the data was right. He checked it again. And then he told someone sitting next to him, quietly, that they were looking at interstellar space. The person next to him stopped typing. That is the moment. Not the press conference, not the paper in Science, not the headline. The moment is a man sitting at a terminal in Pasadena, California, checking a number twice, and then saying something quietly to the person next to him. That is how the species left the solar system for the first time. Not with a countdown or a crowd, with a scientist who wanted to be sure before he said it out loud. Voyager 1 is currently more than 23 billion kilometers from Earth. It is the most distant human-made object in existence. Every day, it travels roughly 1.5 million kilometers further into the interstellar medium. There is no destination. There is no mission end. There is only the going and the signal, growing fainter every year, still arriving, still telling us something true about a place no human being will ever see in their lifetime. We live in an era obsessed with speed and immediacy, with data that arrives in milliseconds and decisions made in seconds. And yet here is this machine, built with slide rules and punch cards, and the kind of sustained institutional attention that entire governments can barely muster today, still alive, still talking, a third of a century after it left home. What Voyager proves, not metaphorically but empirically, is that human beings are capable of commitment to timescales that exceed individual lifetimes. We can make a thing and send it out and wait, and be patient enough to recognize what we're seeing when it arrives. The question that Voyager leaves open is not a technical one. The spacecraft is simple, by modern standards. A computer with less processing power than a digital wristwatch, a golden record that may never be played, a plutonium heartbeat that is slowly going quiet. The question Voyager leaves open is whether we still have the will to make things that will matter in 300 years, in 3,000 years, in 300,000. Whether we can still decide that something is worth doing, even if none of us will be alive to see it finished. If this kind of history, the kind that happens quietly, in data, at the edge of everything, is what you come here for, subscribe. There is more where this came from.
Oh, before you go, if this video made sense to you, subscribe to the channel. This helps YouTube deliver this content to even more people. Also, leave your like. It's essential for our growth here on the platform. And if you want to support us even more, Super Thanks is right below and helps directly with the production of new content. Comment here where you're from. And thank you for watching us until the end. See you in the next video.